So the last section in Chapter 2, dealing with derivatives for Chapter 2, is something called related rates. These are more word problems. So there's a couple steps we're going to follow. So number one, we got to understand the problem after we read it. We got to know what we're dealing with. We got to develop a mathematical model. Sometimes you might have to draw a picture. I'll tell you it's rare, but sometimes you might have to draw a picture to help you see it. You're going to write an equation relating the variables whose rate of change you want to find. And you're going to write an equation for the ones you know. Then we're going to differentiate both sides with respect to t now. So we're sort of going to incorporate a little bit of implicit here. And then we're going to sub in our values and we're going to solve for whatever is being asked to find. So number one says find the rate of change for the area of a circle. So before we move any further, we see area of a circle. We know that formula is pi r squared. Now it says with respect to the radius. So find the rate of change of the area. So that's dA. Because think, dy dx is the rate of change of y with respect to x. That's the derivative. Find the rate of change of the area with respect to the radius. So dA dr. So we are looking for dA dr. We don't know that. Then we're going to evaluate the rate of change of A at r is equal to 5 and r is equal to 10. Okay, so the first thing we want to do, I know it said we're going to differentiate with respect to time. In this particular case, it's different just because there is no time component thrown in here. So there's no time in this problem because it's area with respect to the radius. Okay, so what we're going to do is we're going to take the derivative of both sides. Now, it's with respect to the radius. So I'm going to take my area formula, and then I'm going to take the derivative dA over dr of both sides. And I'm going to check, do the variables agree? These don't. So these do not agree. These do agree. Okay, so think implicit when you're writing this out. So when they agree, we're good. You just take the derivative. So pi r squared, pi hangs out, and the derivative of r squared is just 2r. So that gets us 2 pi r. There's our right side. When they don't agree, though, we have to add, just like with dy dx, or just with y, we had to add the dy dx. So if a and r don't agree, then the derivative of a is 1, and then we have to add dA over dr, because we're taking the derivative of area with respect to the radius. So I can actually, I don't need the 1 there. So I just have dA over dr. So that is my equation now for the rate of change of area with respect to the radius. So now what's nice is they told us, all right, well at r is 5. So now I'm going to take my formula and I'm going to just sub in 5. So when I do that, I get 10 pi. And then I'm going to do the same thing at 10. So dA over dr, 2 pi times 10, which gets me 20 pi. And if I'm taking the radius, or sorry, the area with respect to the radius, so we're evaluating the rate of change of A. So we're talking area here, so we want centimeters squared for these guys. Okay, I'm going to tell you 99% of the time it's going to be with respect to t. But just always read the question, because if there is no reference to time, then obviously it's going to change. And it's not going to be the same as what we're about to go over. All right, so other things we need to know geometric formulas. Area was one of them. This second example, it says it talks about a spherical balloon. And it says the units are cubic feet per minute. So when we're talking cubic feet, we're talking volume here. So you need to know what the volume of a sphere is. So volume of a sphere is 4/3 pi r cubed. So that's the formula. It's telling us that we have 20 cubic feet per minute. Well, if we have 20 cubic feet per minute, that's telling me that I have dV, because volume is associated with feet cubed, over dt, because time is associated with minutes. How fast is the radius of the balloon increasing? So I have the rate of change of the volume with respect to time, but it's saying how fast is the radius of the balloon increasing. So that is dr over dt. The radius with respect to time, that is what I do not know. All right, so what we're going to now, and then we have 2 to work with, but first we have to get the derivative. So we have our formula. So now what we're going to do, if we have v equals 4/3 pi r cubed, so now this is with respect to time, so we are taking, so the variable you're using goes in, say, the numerator, we'll put it that way. So we have dv over dt. Over here, we're going to do dr over dt. The point, though, is the denominator has to be dt. So in neither case, nothing agrees. So does not agree, does not agree. Which means on both sides, we're going to have something. So the derivative of v is 1 dv dt. And the derivative of 4/3 pi r cubed, 3 comes down, and you get 4 pi r squared dr dt. So what do we know? Well, we know dv dt is 20, so I can sub that in. And my goal is to solve for dr dt. So I'm going to divide now by 4 pi r squared. Those values of 1 and 2 should not be subbed in. I'm going to simplify, and my equation for the rate of change of the radius with respect to time is now 5 over pi r squared. And now if I have my equation, now if r is 1, then I just have to take my equation and type it in, and I get 5 over pi. And for b, if r is 2, same thing. You take the same exact equation and you type it in, and you get 5 over 4 pi. Now, the last thing you have to think about is what are the units. So if we are solving for the radius with respect to time, well, if the volume with respect to time was feet cubed per minute, then the radius is going to be feet per minute. So your units should be feet per minute for both of them. Feet per minute. Okay, but most of these are going to deal with time. All right, volume for a cone. So we have that 1/3 pi r squared times h. It says find the rate of change of the volume. So we don't know dv over dt. If the radius is 2 inches per minute, and it's telling us that h is equal to 3r. And then don't worry about the a and the b for right now. So the extra piece that comes in number 3 is we have another variable. We have a third variable thrown in there. So you can only have 2 variables that you can work with at a time. So you can't have 3. So the first thing we're going to do is we're just going to sub in the 3r into the actual equation itself before anything happens. So if I type that in, so I have 1/3 pi r squared times 3r. The 3's cancel. And my new equation is going to be pi r cubed for this particular one. So now what I'm going to do is I'm going to take the derivative with respect to time of the left, and I'm going to take the derivative with respect to time of the right. Again, in neither situation do they agree. So the left is dv dt, and the right I get 3 pi r squared dr dt. What we do know, we do not know dv dt, that's what we're finding, but we know that dr dt is equal to 2, so I can sub that in. So the equation for dv dt is 6 pi r squared. And now what we can do is, well, if r is 6, then dv over dt is 6 pi times 6 squared, which is 216 pi. And for b, if r is 24, then dv over dt is 6 pi 24 squared, which is 3456 pi. And then again, it comes down to the units. So if we're talking volume with respect to time, if radius was inches per minute, then volume is going to be inches cubed per minute. Inches cubed per minute for that. All right, now we're talking about pebbles. So we have pebble that's dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So sometimes if you're struggling, the units help you. So if we're talking feet per second, we're talking about the radius with respect to time. So that's 1 foot per second. When the radius is 4 feet, at what rate is the total area of the distributive water changing? So in this case, we don't know dA over dt. So now what's different, and we know that r is 4. So what's different about 4 and 1 is with number 1, we were only dealing with the area and the radius. In this example, though, the time component has been added into the mix. So you're still going to use the same area formula for a circle. Area equals pi r squared. The only difference is we're not taking the derivative with respect to the radius. We're going to take the derivative with respect to time on both sides, which means nothing agrees. So dA over dt, and we have 2 pi r dr over dt. We know the radius from above, so that means dA over dt is 2 pi r, type in a 1. So that gets us 2 pi r. And then if the question is now asking us, all right, well, what's the rate of change of area with respect to time? We're going to take that 4 for the radius that we were given, and we're going to type that in, and we get 8 pi. And then the units, because it's area with respect to time, is feet squared per second, because a radius was feet per second. So the area would be feet squared per second. All right, 2 more. So we got another sphere. So we have 4/3 pi r cubed. It says, so the volume increases at a rate of 100 centimeters cubed per second. So that's dV over dt, 100 cubic centimeters per second. How fast is the radius? So dr over dt we don't know. And we know the diameter is 50. And if the diameter is 50, we know the radius is 25. All right, so step 1, we're going to take the derivative with respect to time on both sides of the equation. 4/3 pi r cubed, nothing agrees. So dV dt, we get 4 pi r squared dr dt, and we're going to sub in what we know. So we know the volume, and we're looking for the radius with respect to time. So now we're going to divide. We're going to simplify. So dr over dt equals 25 over pi r squared. And now what we can do is we can simplify or sub in our r value. So let me actually do that here. So we get 25 over pi, and then it's 25 squared. So if that's 25 times 25, one of these 25s is going to cancel. So we get 1 over 25 pi. You're going to leave it just like that. And if this is radius with respect to time, if volume was centimeters cubed per second, this is going to be centimeters per second. All right, last and final one, changing it up again. So car A is traveling west, 50 miles an hour. Car B is traveling north at 60 miles per hour. And they're headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 and B is 0.4 miles away from the intersection? Okay, so we're talking miles per hour, so we're with respect to time, so I can make a chart here. So dA over dt is 50 miles per hour. dB over dt is 60 miles per hour. Car A is 0.3 and car B is 0.4. But again, that's not really going to get me anywhere. So what I know is that north and west are perpendicular, so I can finish it and make a triangle out of it. So thinking back to your geometry days, we're thinking Pythagorean Theorem for our equation. Okay, so Pythagorean Theorem, which says a squared plus b squared equals c squared. But now keep in mind, in terms of our triangle, it is 0.3 and is 0.4. It's not how fast they were going. So we have 0.3 squared plus 0.4 squared equals c squared. And when we solve, c comes out to being 0.5. So I know that c is 0.5, which means I'm looking for the change for c with respect to time. So I have all the information. I only have one unknown. So the only formula I can work with is a squared plus b squared equals c squared, and everything is going to be with respect to time. So nothing is going to agree. So the derivative of a squared is 2a dA over dt. B squared is 2b dB over dt. And for c, it's 2c dc over dt. And if you look, that's 2, 4, 6 different variables. But we have 5 out of the 6. So we're not still missing 2 of them.